Now, this will be the last slide in chapter 18, right? Now, previously I have shown to you the ideal gas law equation PV equals to nRT, alright? Okay, this is ideal gas law equation or equation of state in terms of number of mole, right? Now, we may also express it in terms of number of molecules, right? N, dalam sebutan N. Okay, how? Okay, just we know that the number of mole can be expressed in terms of N over Na, isn't it? Where Na is number of Avogadro, alright? So just substitute into the number of mole here in terms of number of molecules. Okay, N over Na, and then we have RT, right? Now here you have a constant R over Na. Okay, because we know that R is constant 8.314 and A is Avogadro, also a constant, isn't it? Alright. Jadi constant bagi constant pun kita dapat constant. Alright. So the constant here is known as K, small k. Okay, and this is known as Boltzmann constant. Alright. So, the Boltzmann constant. Okay, it is there in your calculator. You boleh tengok nilai dia and from your calculator. Alright. So, basically, this value equals to, okay, 1.38. Okay, times 10 to the power of negative 23 joule per Kelvin. Alright, so this is Boltzmann constant. Alright, so kita ada dua bentuk. Okay, one, the ideal gas law in terms of number of mole, and the other one, ideal gas law in terms of number of molecules. Alright. Now, one example on how to apply ideal gas law equation. Okay, a spray can containing a propellant gas at twice atmospheric pressure, 202 kilopascal. Now, I want to make it as the initial temperature, the initial pressure, Kp1 equals to 202 times 10 to the power of 3 Pascal. Okay, ni kilo, K kilo. Having a volume of 125 centimeter cubic. Alright, so this one also I want to make it as initial volume, V1. Okay, so 125 centimeter cubic. Right, dalam liter cubic, ia adalah, okay, times 10 to the power of negative 6 meter cubic. Okay, and then given it is at 22 degree Celsius, right? So 22 degree Celsius in Kelvin, okay, plus it with 273. So we get, okay, 295, okay, 295 Kelvin. Alright, so these are the initial conditions. Alright, it is then tossed into an open fire. Right, so when tossed into open fire, we expect that temperature will increase. Right, so when the temperature of the gas reaches 1 to 5 degree Celsius, right, so T2 equals to 195 degrees Celsius. In Kelvin, it is equals to 468 Kelvin. Right, so the question is, what is the pressure inside the gas? So we are going to find P2, isn't it? Okay, now want to find P2. Now assume any change in the volume of the can is negligible. Alright, so in this case, we are going to assume that the volume is constant, right? V. Okay, dia adalah constant. Now, whenever you have that, okay, when the container, okay, ataupun any bekas, okay, container, if there is no, kita kata apa, if the container is fixed, right, meaning if it is in the form of cylinder, it remain as a cylinder. Okay, kalau bentuk dia tak berubah, so the volume will remain the same. Right, volume pun tak berubah. Kalau tak ada sebarang kebocoran, right, for the can, so we assume that the volume remain constant. If there is no leakage, right, ataupun we took out certain amount of gases from it, then volume will change, right. So in this question, okay, there is no clue saying that we take out a certain amount of gases outside, isn't it? Alright, so the volume remain constant, right. Okay, so nak cari the new pressure, right? So from PV equals to nRT, alright? So pressure berubah, T pun berubah, alright? So V, N dengan R constant, alright? Okay, so therefore we have that P is directly proportional dengan T, or we have P1 over T1 equals to P2 over T2. Alright, so the ideal gas law equation reduced to P1 over T1 equals to P2 over T2. Alright. So P1 is 203 times 10 to the power of 3 Pascal. Okay, T1 is 295 equals to, alright, so P2 nak cari, okay, P2 over T2. T2 is 468 Kelvin. Alright, so daripada sini, can you find P2? Yes, alright, so P2 you get 320. Alright, so here I get, okay, 320 kilo Pascal. Alright.